Hi everybody, this is section 9.42, matrices, day 2, operations. So now that we know what matrices are, let's start adding them up, subtracting, multiplying, dividing. So matrices, sometimes when it asks about the dimensions, it means the number of rows and columns, and in that order. So this is a 2 by 3 matrix, as we saw yesterday in the last video. This is a 3 by 3, this is a 2 by 1, because it lists the number of rows and then the number of columns, like I said, in that order. Now, if you had two matrices that you wanted to add to each other, they would have to be the exact same dimensions. This one is a 3 by 2 plus another 3 by 2 yields another 3 by 2, and you just add the corresponding digits. 1 plus -1 is 0. 6 plus -3 is positive 3. Add everything that are corresponding. So that's not too hard to do. Scalar multiplication is basically a regular number times a matrix, and so that's one kind of multiplication. You can see the 5 kind of distributes to all the different elements in the matrix. 5 times 1 is 5, 5 times x is 5x, 5 times x squared is 5x squared. And you just put them in the same location. Fine, scalar multiplication. Now, what gets... and maybe you've even seen these before in previous math classes. I know personally I was introduced to matrices much earlier, like 4th, 5th, 6th grade, and that's what we see. Maybe not 6th grade, maybe like 7th grade. In any case, so multiplying matrices is is much more difficult and tricky, and so if you have a matrix A and you multiply it by a matrix B, you can get a matrix C. This is what it looks like. Matrix A is here, matrix B is here. And what I've decided to do to kind of help understand why you're multiplying and adding in such a strange and complex way, I wanted to do it in terms of a word problem. So matrix B shows the number of calories burned by two different people of two different weights doing different activities. So you've got a 120-pound person and a 150-pound person. This is, they both go biking, they both go jogging, they both go walking. This is number of calories per minute. As you can see right here, here are the units. Matrix A shows the times that two people spend on each activity. So they're both doing this together. They both bike 40 minutes, and then they jog 10 minutes, and then they walk 60 minutes. So the question is, how many total calories does each person burn? We know they're going to burn different amounts because they weigh different. They have different weights, and so although they have similar times, they're going to burn different amounts of calories. So this is going to be just the perfect setup for multiplying matrices. If we multiply A, the entire matrix A times the entire matrix B with the entire matrix C, I'll tell you what the answer is. This is what it looks like. And you'll notice that the dimensions are not the same as either of the individual, like the first two. So matrix A was a 1 by 3 matrix. We see 1 row by 3 columns. And matrix B was a 3 by 2, 3 rows by 2 columns. And the product is going to be C, which is a 1 row by 2 column matrix. And the funny thing about matrix multiplication is that these middle numbers, these middle dimensions, disappear. You start off with a 1 by 3, and then you multiply by 3 by 2, and so they disappear. You keep, and if you want to figure out what the resulting matrix would be, you keep the first one and the last one. So it's a 1 by 2. You can see it's color-coded. And in fact, you're actually not even able to multiply matrices unless these inner dimensions are the same. So you can't multiply a 1 by 3 by a 2 by 3 because then the process I'm about to show you won't even work. So I've color-coded things down here. Everything that has to do with biking is peach orange. Everything that has to do with jogging is kind of this aqua green, and everything that has to do with walking is purple, indigo. I really don't know my colors. Maybe you guys could help me out. My wife helps me out. All that stuff. Precise naming of colors. In any case, you can see biking, jogging, walking. Biking, jogging, walking. Now, if you want to figure out how many calories person A, the 120-pound person you would burn, you'd have to figure out how much they do by biking. So you multiply the 40 times the 5.45 here. Then you figure out their jogging calories. That's the 10 times the 6.35 here. Then you multiply the walking calories times their time. That's 60 times 3.2. Calories per minute times time in minutes is going to give you calories. And so these are the total biking calories, jogging calories, walking calories, and you add them all up to get a grand sum total of 473.5. And there it is. You can repeat the process again for the 150-pound person, biking, jogging, walking, and you put their total right here. It's equivalent to, like, I wanted to tell you the story just so you kind of understand why things are the way they are, and I hope the setup in the units and the story about people biking and jogging and walking help you understand how to calculate what you need to calculate. But even if there weren't a story like that, you would still do the exact same thing. You would take this I'm going to completely eliminate all story and just do complete numbers. If you want to take this 1x3 matrix and multiply it by this 3x2 matrix, you're allowed to, because the inner dimensions 3 are equal. This has 3 columns and this one has 3 rows. Great. So you can't multiply them in the other order. That's the other thing. Like, it has to be in this particular order. You can't just take these two matrices and say B times A, because then the process wouldn't work out. You wouldn't be able to multiply exactly what I'm multiplying now. But in any case, you would multiply this times this, and you get these two answers. In fact, you can type these into Symbolab, or you can type these into a TI Inspire, and it should be able to produce out these exact numbers right here. Let me give you, so like I said before, A times B is equal to C. Let's note a couple of things. First of all, here, in this new matrix, in this new problem, this is a 4x3, so 4 rows by 3 columns. This is a 3x1 matrix here, and so the resulting matrix is going to be a 4x1 matrix here. Any notion of the dimensions of 3 are going to kind of be lost. And I will also note, in the answer, any notion of biking, jogging, or walking, or any distinction between those gets lost as well. We still can differentiate these two people. We know this column has to do with a 120-pound person, and this column has to do with a 150-pound person, and we know that's time. But it's all, like, the separation between biking, jogging, and walking has been lost, and we just have these here. As you can see, the dimensions disappear. Same thing here. We have different data on wheat, rice, and maize in the original matrices, but in the final matrix, it's all going to get washed out. We're going to have 4 countries: China, India, Russia, USA, and then we're going to have 1 column representing the total metric tons. I'll just read this. Matrix A over here shows each country's percentage of worldwide production for 3 different grains. So China produces 20.1% of all the wheat. They produce 34.8% of all the rice and 18% of all the maize. Same thing for USA. USA produces 11.3% of all the wheat, 1.4% of all the rice, and 40.5% of all the maize. Great. And if you want to know a particular year, in this, I forget what year it was, I got this example, it's like in the late 90s. Here we've got total metric tons. In the whole world, there are 609 metric tons of wheat being produced one particular year, 571 metric tons of rice in that particular year, and 587 metric tons of maize in that particular year. So if you want to figure out how many total tons of grain in each country, you can multiply these two matrices together. Notice over here for the matrix multiplication, I convert everything to a decimal by moving the decimal place over twice. And you could type it into your Symbolab or into TI Inspire just this way and get out this answer. But if you want to know why you're doing what you're doing or how it calculates those numbers, you take the percentage of China wheat and multiply it by the total amount here. 20.1% of 609, that's going to be our result here. And then China is also going to be producing some rice. 34.8% of 571. That'll be added up also. And then China's maize. So this is China's wheat, China's rice, and China's maize. It all gets added up, and we can see that China, in this particular year, produced 427 metric tons of grain total. We don't know what kinds of grain. That get lost in the calculations. And you can repeat the same thing for the other countries as well. You can see this down here is the USA, 11.3% wheat times 609, and so forth, and to get a total of 315 metric tons of grain. So when you multiply these two matrices together, you get the total tons of grain in each country. Now, I said it before, I'll say it again. If you were going to try and reverse this order, notice you can't necessarily multiply a 3 by 1 matrix times a 4 by 3 matrix. It's just not commutative. It's just very strange because we normally think of multiplication as commutative, like, I don't know, 2 times 5 is the same thing as 5 times 2. You can switch those. But you know what? Division isn't commutative. 10 divided by 2 is not the same thing as 2 divided by 10. So things not being commutative is not that strange. Subtraction is not commutative. 5 minus 1 is not the same thing as 1 minus 5. So here, you have to put matrix multiplication in that category also of not being commutative. You can't just flip the order, even if the dimensions are the same. Like I've been saying before, that you can't do this because the 1 and the 4 aren't matching up. Even if you had matrices C and D, each of having the same dimensions, a 2 by 2 and a 2 by 2, and the result is also going to be a 2 by 2. You can't even say that they're going to be equal, even though you can compute C times D, the matrices, and the matrices D times C. You can compute these. They're not going to necessarily be equal. There's some isolated cases where they happen to be equal, but you can't say that they are exactly equal in all cases. So here, one of the big reasons why we talk about matrix multiplication is related to solving equations. Check this out. If you wanted to solve this, we know that you could put it in row-reduced echelon form and get an answer, and that's fine. But there are lots of other tricks that are related to matrix multiplication and systems of equations that, and I just want to open up the door here. So if you take all the coefficients, just a 3 by 4, just the 4, the 2, the negative 1, the 9, the 0, the 1, the 4, the 5, the negative 2, 1, 1, 1, and you put them all here, you could consider that to be a coefficient matrix of A here. And then if you had x, y, and z, that would be the variables. And if you were to multiply these two together, you would get the answers. Notice there'd be 4 times x plus 2 times y times negative 1 times z. And you put it all here, you add them all up. 9 times x is 9x, 0 times y is 0, and 1 times z is z. So, and you continue going from each one of these equations, you've got the variables, and so the distinction between all the variables gets lost, and what you're left with is just the answer, 3, 5, 1, 0, to all the equations. I want you to tell me what you think goes here. This is 3, 5, 1. You've got the equations here all equaling particular constants. Now this is incredibly powerful because what you can do is you can you're basically like isolating all the variables into one matrix, and you can and we're not going to do this in this particular video. In fact, I haven't even given you the audio check yet. It's Shakespeare in Love, 1999. I don't mind dating myself. This is the year I graduated from high school. It's a fabulous movie, really fun, romantic, kind of like romantic comedy, but also set in Shakespeare's time. And anyone who has read Romeo and Juliet, which is pretty much anyone who's ever gone to high school in the United States in 9th grade, will have read it, and I think you'll appreciate it. So check it out, Shakespeare in Love, 1999. We're not going to do this in this particular video, but I am going to say that there's lots of things you can do with this equation. I am going to say that's enough for now. Let's start 92, do the first problem, and I will see you in class. Shoot me an email if you got any questions.